On October 29th, 2025, something happened behind the sun that Harvard's most controversial astrophysicist believes could change everything we understand about our place in the universe. While Earth's telescopes were blind to what occurred during those hidden hours, Avi Loeb claims an interstellar visitor may have executed a maneuver so precise, so strategically calculated, that natural explanations face serious challenges when accounting for mathematical improbability. How is that even possible? Think about what it means for an object to pass behind the Sun at perihelion, the closest point in its orbital approach, at the exact moment when human observation becomes impossible. Think about what it means when that same object brightens dramatically, shifts colour to an unexplained blue, and emerges on a trajectory that aligns with not one, not two, but 3 planetary bodies in our solar system, with a probability so vanishingly small that the mathematical framework invites us to ask whether random chance alone accounts for the pattern, or whether an intentional trajectory optimization provides a simpler explanation. This isn't speculation wrapped in fantasy. This is peer-reviewed astrodynamics colliding with observations that refuse to fit the narrative we've been comfortable accepting. The object is 3I Atlas, the third confirmed interstellar visitor to our solar system, and it's been defying expectation since the moment astronomers began tracking its behaviour. Unlike the silent, tumbling mystery of Oumuamua or the well-behaved ice ball of 2I/Borisov, this visitor has displayed characteristics that split the scientific community down the middle. Some see a comet with unusual but explainable features. Others see something that shouldn't exist according to our current understanding of natural celestial mechanics. And Avi Loeb, the man who first proposed that Oumuamua might be an alien light sail, sees something far more provocative, an object that's not just passing through our solar system, but actively using it. Taking advantage of the sun isn't poetic language. It's a technical description of what advanced spacecraft would do if they needed to decelerate, adjust trajectory, or harvest energy while traveling between star systems. It's called a solar obath maneuver, and if you're an intelligent civilization crossing the vast emptiness between stars, the sun isn't just a navigation hazard, it's a strategic resource. The timing of October 29th wasn't arbitrary. The alignment with Venus, Mars, and Jupiter wasn't random, and the fact that 3I Atlas executed this perihelion passage while completely hidden from Earth's observation, that's either the most convenient accident in astronomical history, or it's exactly what you'd expect if something didn't want us watching. Now, I know what you're thinking. This sounds like the setup for another fringe conspiracy theory. Another reaching attempt to inject aliens into phenomena that science can adequately explain with patience and data. I understand that skepticism, I share it. But here's what makes this different. The mathematics don't lie, the observations are documented by multiple independent sources, and the peer-reviewed research outlining these trajectory anomalies exists. You can read it yourself. The question isn't whether something unusual is happening with 3I Atlas that's already established. The question is whether we're intellectually honest enough to follow the data wherever it leads, even when it leads somewhere uncomfortable. Before we go further, I need you to do something. If this topic interests you, if you're the kind of person who reads past headlines, who demands evidence before judgment, who understands that legitimate scientific inquiry sometimes ventures into territory that makes institutions nervous, then subscribe to this channel and turn on notifications. Not because I'm asking for engagement metrics, but because what unfolds over the next 45 minutes requires the kind of community that thinks critically. What I'm about to show you isn't something mainstream outlets will touch until they're forced to. They're waiting for official statements, for institutional permission to discuss what's already visible in the data. But you and I, we're going to examine the evidence now, while it still matters, while predictions can still be tested. Between now and December the 5th, 2025, we have a verification window. If Avi Loeb's hypothesis about 3I Atlas holds, if this object is following an intelligently optimized trajectory, rather than a natural ballistic path, then specific observable events should occur during late November and early December. The object should maintain non-gravitational acceleration. Its brightness and spectroscopic signature should remain anomalous, and its approach vector should continue aligning with planetary positions in ways that gravitational mechanics alone cannot explain. We're not talking about vague predictions or unfalsifiable claims. We're talking about testable, observable, falsifiable hypotheses that will either hold up or collapse under scrutiny within weeks. So here's what we're going to do. We're going to start with who Avi Loeb is and why his voice carries weight despite controversy. Then we'll examine what makes 3I Atlas different from every other comet and interstellar object we've observed. We'll dive into the October 2nd Mars encounter that produced an image NASA apparently hasn't released. We'll break down the orbital mechanics of solar obath maneuvers and why October 29th was the optimal execution date. We'll look at the planetary alignment probabilities that defy coincidence. And we'll discuss what happens next, what you should be watching for, what observations would confirm or refute this hypothesis, and why institutional science might be hesitant to discuss any of this publicly until they're certain. This isn't about believing in aliens. This is about demanding that extraordinary observations receive extraordinary investigation. Let's begin. If you're going to evaluate controversial claims about interstellar objects behaving in ways that suggest intelligence, you need to know whose claims you're evaluating. Avi Loeb is not a fringe blogger chasing clicks with sensational headlines. He's the Frank B. Baird Jr., professor of science at Harvard University, former chair of Harvard's astronomy department, founding director of Harvard's Black Hole Initiative, and director of the Institute for Theory and Computation at the Harvard Smithsonian Center for Astrophysics. He's published over 1,000 academic papers, mentored dozens of doctoral students, and served on numerous advisory committees for NASA, the National Academy of Sciences, and international space agencies. When Avi Loeb speaks about astrophysics, astrodynamics, or the search for extraterrestrial intelligence, he speaks from a foundation of institutional credibility that few scientists can match. But credibility and controversy are not mutually exclusive, and Loeb has become as famous for challenging scientific orthodoxy as he has for his academic achievements. His willingness to publicly discuss the possibility that Oumuamua, the first confirmed interstellar object detected in 2017, might be an alien probe rather than a natural asteroid, made him both a media sensation and a target for criticism within the astronomical community. Colleagues accused him of speculation beyond the data, of seeking attention, of damaging the credibility of serious SETI research by lending his name to ideas that couldn't be proven. And those criticisms weren't entirely unfair. Loeb did make claims that outpaced the evidence. He did present the alien hypothesis as more viable than many of his peers believed the data supported. Yet here's what his critics often miss. Loeb was also right about the anomalies. Oumuamua did exhibit characteristics that natural models struggled to explain: its extreme elongated shape, its non-gravitational acceleration without visible outgassing, its unusual brightness variations, and its hyperbolic trajectory that suggested origin from outside our solar system. These weren't fabrications. These were documented observations that remain to this day inadequately explained by conventional comet or asteroid models. Loeb's sin wasn't noticing the anomalies. His sin, in the eyes of institutional science, was suggesting publicly that we should seriously consider non-natural explanations when natural ones prove insufficient. This tension is important because it frames how we should receive his claims about 3I Atlas. Loeb operates at the intersection of rigorous scientific methodology and intellectual risk-taking. He demands data, peer review, and mathematical precision. But he also refuses to prematurely dismiss hypotheses simply because they make people uncomfortable. Most scientists wait until they're certain before speaking publicly. Loeb speaks publicly to invite scrutiny that will either strengthen or dismantle his hypotheses. It's a different approach to scientific discourse, one that prioritizes transparency and public engagement over institutional gatekeeping. When Loeb talks about 3I Atlas, taking advantage of the sun, he's not making idle speculation. He's referencing peer-reviewed research he co-authored with colleagues Hibbard and Krell, examining the orbital mechanics and non-gravitational acceleration patterns of this object. The paper exists, the calculations are documented, the observations are reproducible. You can disagree with his interpretation, but you can't dismiss him as someone making things up. He's operating within the boundaries of scientific methodology, while venturing into interpretive territory that most of his colleagues avoid. And that's precisely why you should listen, not because he's necessarily correct, but because he's forcing questions that need asking. If 3I Atlas is just a comet, then why does it display an antitail when comets don't produce antitails through known mechanisms? If it's outgassing naturally, why don't spectroscopic observations detect the chemical signatures we'd expect? If its trajectory is purely gravitational, why does its alignment with Venus, Mars, and Jupiter occur with a probability of 0.005% 1 in 20,000? These aren't rhetorical games. These are legitimate scientific questions that deserve investigation regardless of where the answers lead. Loeb has also demonstrated something else crucial. He's willing to be wrong publicly. After Oumuamua, when further data failed to support some of his more speculative claims, he didn't double down or move the goalposts. He acknowledged what the data showed and adjusted his positions accordingly. That's not the behavior of a charlatan or a conspiracy theorist. That's the behavior of a scientist who understands that hypotheses exist to be tested, not protected. His track record shows someone who values truth over ego, which is precisely the kind of person you want making provocative claims, because you can trust he'll follow the evidence wherever it goes. The reason institutional science distrusts Loeb isn't because he's wrong about the data. It's because he refuses to whisper about possibilities that should be shouted. The scientific establishment prefers caution, qualified language, and conclusions that arrive only after exhaustive peer review and consensus building. Loeb prefers urgency, public discourse, and inviting the world to watch science unfold in real time. Both approaches have value. But when we're talking about an interstellar object that may be executing maneuvers behind the sun, waiting for institutional consensus might mean waiting until the object is long gone, and the opportunity for real-time observation is lost forever. So when you hear Loeb's claims about October 29th and what happened during 3I Atlas's perihelion passage, you're hearing from someone who has earned the right to be taken seriously, even when, perhaps especially when, he's saying things that sound impossible. He's not asking you to believe him. He's asking you to look at the data, examine the mathematics, and decide for yourself whether the simplest explanation is really the correct one. And that's a challenge worth accepting. Which brings us to the object itself, what makes 3I Atlas so fundamentally different from everything else we've observed crossing our solar system, and why its behaviour has fractured scientific consensus into camps that can barely speak to each other without accusation. Now, before we move to the October 2nd encounter, I need to acknowledge the mainstream scientific response. Most astronomers attribute 3I Atlas's anomalies to natural cometary processes. The anti-tail can result from specific dust particle behaviours and observational geometry. The spectroscopic silence might indicate unusual composition or viewing angle effects rather than absence of outgassing. The brightness variations correlate with solar heating, even if the exact mechanism differs from typical comets. The non-gravitational acceleration is likely from directional outgassing jets, a documented comet behaviour called the rocket effect. The planetary alignments, while improbable, aren't statistically impossible. None of these individual explanations are rejected by mainstream science. The debate isn't whether anomalies exist, they're documented. The debate is whether they form a coherent pattern requiring new mechanisms, or whether they're coincidental, unusual but natural features of a comet from an alien star system. Understanding that distinction matters. Let's establish what 3I Atlas is without retreading ground you already know. You understand it's an interstellar object, the third confirmed visitor from beyond our solar system. You know its trajectory is hyperbolic, meaning it's not gravitationally bound to the sun and will eventually leave our system entirely. What you need to understand now is what makes it anomalous, not just unusual, but persistently, documentably, mathematically inconsistent with natural comet behaviour in ways that demand explanation. First, the anti-tail. Comets produce tails through sublimation ice turning directly to gas as solar radiation heats the comet's surface. This gas and dust gets pushed away from the sun by solar wind and radiation pressure, creating the characteristic tail that always points away from the sun regardless of the comet's direction of travel. It's one of the most predictable phenomena in observational astronomy. But 3I Atlas displayed something different, an anti-tail, a structure pointing toward the sun rather than away from it. Now, anti-tails aren't completely unknown. They can occur when Earth's viewing angle creates an optical illusion, making it appear that dust particles are pointing sunward when they're actually in the comet's orbital plane. But that explanation requires specific geometric alignment between Earth, the sun, and the comet. For 3I Atlas, that alignment didn't exist during the periods when the anti-tail was observed. Multiple independent observers documented this feature from different locations, ruling out viewing angle artifacts. So if it's not an optical illusion, what's producing a structure that points toward the sun? The standard answer would be dust particles on unusual orbital trajectories, perhaps influenced by the comet's rotation or outgassing jets. But that explanation requires outgassing, which brings us to the second anomaly, spectroscopic silence. When comets approach the Sun and begin sublimating, they produce characteristic emission line signatures of water vapour, carbon dioxide, hydroxyl radicals, and other volatiles. These signatures are how we confirm something is a comet rather than an asteroid. They're also how we determine composition, outgassing rates, and activity levels. For 3I Atlas, these signatures have been conspicuously weak or absent during periods when, based on solar distance and brightness, the object should be vigorously outgassing. It's behaving like an active comet in terms of brightness changes and structural features, but it's not producing the chemical evidence of cometary activity. You can explain this in several ways. Maybe the object's composition is unusual, perhaps it's made of materials that don't sublimate at the temperatures it's experiencing. Maybe the outgassing is highly directional, aimed away from Earth's line of sight. Maybe the object is covered in a dark insulating crust that limits sublimation to specific areas. All plausible, all possible. But each additional maybe you stack on top of the previous one decreases the overall probability that you're dealing with a normal comet that just happens to have several unusual characteristics simultaneously. Then there's the brightness behaviour. Comets brighten as they approach the Sun and fade as they recede. This is expected and well modelled. But 3I Atlas underwent rapid brightness changes that didn't correlate cleanly with solar distance. It would brighten unexpectedly, then plateau, then brighten again. Observers noted periods where the object appeared significantly brighter than models predicted, followed by periods where it dimmed faster than expected, and during its October 29th perihelion passage, it brightened dramatically and shifted colour toward blue, a change that suggests either compositional differences in sublimating material or something else entirely. Blue coloration in cometary activity typically indicates the presence of specific molecules like carbon monoxide or diatomic carbon, which emit in blue wavelengths when excited by solar radiation. But again, if you're seeing blue emission, you should also be detecting the corresponding spectroscopic signatures. For 3I Atlas, the blue brightening occurred without the expected chemical fingerprints. It's like watching someone light a fire that produces coloured flames without any fuel source you can identify. Something is causing the brightness and colour change, but the mechanism remains unclear. Now layer on the fourth anomaly, trajectory. Interstellar objects should follow trajectories determined purely by gravity, the Sun's gravitational pull, planetary influences, and their own incoming velocity. Once you calculate those factors, the path is predictable. But 3I Atlas has exhibited non-gravitational acceleration, subtle changes in velocity that can't be explained by gravitational forces alone. This is the same behaviour that made Oumuamua so controversial. For a comet, non-gravitational acceleration usually comes from outgassing jets as material sublimes and ejects from the surface. It acts like a tiny rocket engine, pushing the comet slightly off its gravitational trajectory. This is called the rocket effect, and it's well documented in cometary science. But here's the problem. The magnitude and direction of 3I Atlas's non-gravitational acceleration don't match what you'd expect from random outgassing jets. Outgassing produces acceleration that varies based on the comet's rotation, surface composition, and solar heating. It's chaotic, unpredictable, and changes as different parts of the surface face the Sun. For 3I Atlas, the acceleration has been consistent and directional in ways that suggest it's not random. It's almost as if the object is making course corrections. Now, that's a loaded statement, and I'm not claiming definitive proof of intentionality. What I'm saying is that the pattern doesn't fit the chaos we expect from natural outgassing. It fits the pattern you'd see from controlled thrust. And then we arrive at the planetary encounters. 3I Atlas made a close approach to Venus, then Mars on October 2nd. Its trajectory then aligned in such a way that Jupiter's gravitational influence would become significant. For a random interstellar object on a hyperbolic trajectory, encountering multiple planets is possible but statistically unlikely. Encountering them in sequence with approach distances that allow for significant gravitational interaction requires a trajectory so precisely calibrated that the probability calculation becomes uncomfortable. We're going to dive deep into those numbers in a later section, but for now understand this. When independent factors compound antitail, plus weak spectroscopy, plus unusual brightness, plus non-gravitational acceleration, plus planetary alignments, you reach a point where coincidence becomes a less parsimonious explanation than design. This is why 3I Atlas matters in a way that previous interstellar objects didn't. Oumuamua was anomalous but distant and brief. 2I/Borisov was well-behaved and clearly cometary. 3I Atlas is neither. It's exhibiting enough unusual behaviours simultaneously that dismissing all of them as unrelated coincidences requires ignoring the cumulative improbability. And when Avi Loeb looks at this object and says it might be taking advantage of the sun, he's not inventing mystery, he's responding to mystery that already exists in the data. The question isn't whether 3I Atlas is strange. The question is whether we're willing to seriously investigate just how strange it might be. Which leads us directly to October 2nd, and the image that apparently hasn't been released an encounter with Mars that could provide crucial context for everything that happened on October 29th. On October 2nd, 2025, 3I Atlas made its closest approach to Mars, passing within a distance that brought it into optimal range for observation by the Mars Reconnaissance Orbiter's HiRISE camera, the most powerful imaging system currently deployed around another planet. HiRISE is capable of resolving features as small as 1 meter across on the Martian surface from orbital altitude. When pointed at objects in space rather than the surface below, it becomes one of the most sophisticated telescopes available for solar system observation. And according to Avi Loeb, HiRISE captured an image of 3I Atlas during this encounter. An image that, as far as public records show, has not been released. Note: October 2025 saw significant federal government shutdowns affecting NASA operations. Image processing activities aren't mission-critical during shutdowns, so observations were delayed. This bureaucratic delay is the most straightforward explanation for why the image hasn't appeared yet. Now let's be precise about what we know and what we are inferring. We know 3I Atlas passed within range of Mars-based observation on October 2nd because its trajectory is documented and publicly available through orbital tracking databases. We know HiRISE is operational and regularly conducts observations of asteroids, comets, and other solar system objects as part of its extended mission. We know that photographing interstellar visitors is a high-priority scientific objective because such opportunities are rare and the data is invaluable. What we don't know, what hasn't been publicly confirmed, is whether HiRISE actually captured an image, and if so, what that image shows. Loeb has referenced this observation multiple times in interviews and public statements, suggesting that the image exists and that its contents are significant enough to warrant attention. But when you search NASA's public image databases, when you look through HiRISE's released observation catalogue, you don't find it. Why not? The most generous explanation is timing and bureaucracy. NASA operates on review protocols that can delay public release of imagery for weeks or months, while scientists analyze the data, verify calibration, and prepare contextual documentation. Images aren't just dumped into public databases the moment they're received from spacecraft. They go through processing pipelines, quality checks, and scientific interpretation before release. If HiRISE imaged 3I Atlas on October 2nd, it's entirely possible the data is still working through this pipeline and will be released when ready. Patience, in this scenario, is warranted. But let's consider alternative explanations, because this is where institutional behaviour intersects uncomfortably with public curiosity. October 2025 saw significant disruptions in US federal operations, including NASA, due to budget impasses and partial government shutdowns. During such periods, non-essential personnel are furloughed, and only mission-critical operations continue. Science data processing and public release activities are rarely considered mission-critical, so it's plausible that the image exists, was received, but hasn't been processed or released simply because the people responsible for doing so weren't working. Bureaucratic delay, not conspiracy. Yet there's a third possibility that can't be dismissed. The image shows something that requires careful consideration before public release. Not because it's definitive proof of alien technology, NASA wouldn't suppress that if they had it. The scientific and public relations value would be too enormous, but because it shows something ambiguous enough to generate controversy without providing clarity. Imagine an image showing 3I Atlas with unexpected structural features, unusual reflectivity patterns, or geometric characteristics that don't fit cometary norms but also don't prove artificial origin. Releasing that image without thorough analysis and contextual explanation would trigger exactly the kind of speculative firestorm that institutions spend careers trying to avoid. And here's why that matters. The October 2nd encounter was crucial for trajectory validation. By imaging 3I Atlas from Mars orbit at close range, scientists could resolve surface features, measure rotation rates, analyze brightness distribution, and refine calculations of the object's size, shape, and composition. All of this data feeds into models that predict what should happen during perihelion on October 29th. If the Mars observations revealed characteristics inconsistent with natural cometary structure, say, unexpected symmetry, reflectivity variations suggesting manufactured surfaces, or geometric features that don't arise from gravitational accretion and erosion, then scientists would know before perihelion that something unusual was approaching the Sun. Now think about the timing. October 2nd is 27 days before October 29th. If you're an institution like NASA and you've just obtained imagery suggesting an interstellar object might be artificial, what do? You don't immediately release it to the public because you need verification. You need independent analysis. You need to rule out instrument artifacts, processing errors, and misidentification. You need time to build a bulletproof case before making any public statement, because once you say this might be artificial, you can't unsay it. The geopolitical, social, and scientific ramifications of that announcement require absolute certainty, not 80% confidence. So if the October 2nd image showed something ambiguous, something that raised questions without answering them, NASA would face an impossible choice: release it immediately and deal with uncontrolled speculation, or hold it back until additional data from the October 29th perihelion observation could provide context. Institutional incentive favours waiting. Scientific caution favours waiting. Risk management absolutely favours waiting. But transparency and public trust argue for immediate release. Avi Loeb's frustration with this situation is palpable in his public statements. He's argued repeatedly that the scientific community and the public have a right to see observational data as soon as it's collected, especially when that data pertains to objects of historic significance like interstellar visitors. He's accused NASA of excessive caution that borders on gatekeeping, preventing independent researchers from analysing data that could confirm or refute controversial hypotheses. And he's pointed out that delays in data release create information asymmetries, where institutional scientists have access to observations that the broader scientific community doesn't, allowing them to shape narratives before anyone else can examine the evidence. Is he right? Partially. NASA's policies on data release are designed to balance scientific rigour with public transparency, but they do create delays that can feel like suppression when dealing with time-sensitive, high-interest phenomena. The HiRISE team has a documented history of relatively prompt public release of imaging data, typically within weeks to a few months of acquisition. If the October 2nd image hasn't appeared by now, that's either because it doesn't exist, because government shutdowns delayed processing, or because the image shows characteristics that require scientific interpretation before public release. If the image revealed unexpected structural features, scientists would need to verify whether those are actual observations or instrument artifacts before going public, because announcing anomalies, then retracting them, damages credibility more than delayed confirmation. What would that image show if it were released tomorrow? We can speculate based on what we know about 3I Atlas's characteristics. It would likely show an elongated or irregular object. Most small celestial bodies are not spherical. It would show brightness variations across the surface, indicating either compositional differences or topographical features casting shadows. It might show evidence of outgassing if any was occurring at that distance, appearing as bright plumes or jets. And if Loeb's suspicions are correct, it might show something else: regularities in shape, unexpected reflectivity, or structural features that natural processes struggle to explain. But we don't have the image, we have its absence. And in that absence lives a question that feeds directly into the October 29th perihelion mystery. Did NASA observe something on October 2nd that changed how they prepared to observe October 29th? Did the Mars encounter provide advance warning that the Sun encounter would be extraordinary? We can't answer that without the data. What we can do is note the timing, note the silence, and note that when an object passes behind the Sun less than a month after a close-range imaging opportunity that hasn't been publicly disclosed, the gap in information becomes itself informative. It tells us that something about 3I Atlas has made institutions hesitant, and hesitancy in science usually means uncertainty, and uncertainty means we're looking at something that doesn't fit the models. Which brings us to the models themselves specifically, the orbital mechanics of how an intelligent object would use the Sun not as a hazard, but as a tool. Before we explore Loeb's hypothesis, I need to establish proper context. The peer-reviewed paper by Loeb, Hibbard and Crowell that outlines this analysis explicitly states in its opening, by far the most likely outcome will be that 3I Atlas is a completely natural interstellar object, probably a comet. The authors themselves emphasize this is a pedagogical exercise examining trajectory anomalies and asking what if. Rather than presenting artificial origin as probable, they're asking whether the mathematical framework justifies serious investigation despite the overwhelming likelihood of natural explanation. Understanding that distinction is crucial, we're not exploring a confirmed hypothesis, but examining why some data patterns warrant examination, even though mainstream explanations remain statistically favoured. Now, which brings us to understanding the physics of the obath effect. If you're going to understand why October 29th matters, why that specific date, why perihelion, why the timing of 3I Atlas's closest solar approach is so significant to Loeb's hypothesis, you need to understand the physics of the obath effect and how it applies to interstellar navigation. This is the technical heart of the taking advantage of the sun claim, and it's where speculative interpretation meets rigorous astrodynamics. The obath effect is a principle in orbital mechanics discovered by German physicist Hermann Obath in the 1920s. It describes how a spacecraft can gain more kinetic energy from a propulsive burn when that burn occurs at high velocity rather than low velocity. Here's the counterintuitive part. If you have a fixed amount of fuel and thrust, you'll achieve a greater change in your orbital energy by burning that fuel when you're moving fast, like at perihelion, the closest point to the sun, than when you're moving slowly farther away. The faster you're moving when you apply thrust, the more efficiently you convert fuel into kinetic energy. Think of it this way. Imagine you're on a bicycle coasting down a steep hill. If you pedal while coasting at high speed, you add more energy to your motion than if you pedal while climbing slowly up the hill, even though you're applying the same muscular effort. The obath effect is the orbital version of that principle. When a spacecraft is deep in a gravity well, moving at high speed, applying thrust multiplies the energy gain compared to the same thrust applied in deep space where velocities are lower. Now apply this to interstellar travel. If you're an object entering a star system at high velocity, let's say you're coming from another star, travelling at tens of kilometers per second, and you want to slow down, decelerate, or change your trajectory significantly, the most efficient place to do that is close to the star at perihelion. You're moving fastest there because gravity has accelerated you inward. Any thrust you apply at that moment, whether it's from chemical rockets, ion drives, or whatever propulsion technology you possess, will have maximum effect on your trajectory. You get more change in velocity per unit of fuel or energy than you would anywhere else in your path through the system. This is called a solar obath maneuver when applied to using the sun as the gravitational anchor. Spacecraft designers have proposed using this technique for missions to the outer solar system, or even interstellar precursor missions dive close to the sun. Apply thrust at perihelion and use the combined effect of gravity and propulsion to slingshot outward at high speed. It's theoretically very efficient. But there's another version of this maneuver that's less discussed, because human spacecraft rarely need it: the reverse solar obath maneuver. Instead of using perihelion thrust to accelerate and sling outward, you use it to decelerate and adjust trajectory inward. This is what you'd do if you were an interstellar object that needed to slow down relative to a star system, if you wanted to enter a more circular orbit, if you wanted to approach a planet without shooting past it too fast, or if you needed to make course corrections that natural gravity alone wouldn't provide. And here's where 3I Atlas becomes fascinating. Its trajectory brought it to perihelion on October 29th, at a distance of approximately 1.35 astronomical units, closer than Mars but farther than Earth. That's not an extreme perihelion. Comets often come much closer, but it's close enough that if the object applied any thrust, any propulsive force at that point, it would achieve maximum efficiency in altering its post-perihelion trajectory. And what do we observe after October 29th? Non-gravitational acceleration continuing in a pattern consistent with trajectory adjustment, not random outgassing. Let's be specific about what taking advantage of the sun means in this context. Loeb isn't suggesting 3I Atlas is harvesting solar energy in some mysterious way, though that's also theoretically possible for an advanced spacecraft. He's suggesting something more concrete, that the object used perihelion as a strategic point to apply propulsion either to decelerate, to adjust its outbound trajectory towards specific planetary encounters, or both. The sun isn't just a gravitational landmark in this scenario, it's a tool, a fixed point of reference around which efficient maneuvers can be executed. Why execute such a maneuver behind the Sun, hidden from Earth observation? There are two possible answers, and neither requires assuming malicious intent. The first is purely geometric. Perihelion happens where it happens based on the incoming trajectory. If your optimal point for propulsive maneuver occurs on the far side of the Sun relative to Earth, that's just geometry. You don't get to choose when Earth is watching. The second answer is more speculative but worth considering. If you're an object that wants to minimize observation during a crucial maneuver, perhaps because you're testing whether intelligent life in this system is capable of detecting your presence, you'd time your approach so perihelion occurs when Earth's telescopes are blinded by the Sun. You'd execute your maneuver during the observation blackout. Now, before you dismiss this as science fiction, remember that we do this ourselves. Military satellites execute maneuvers during ground station blackouts to minimize observation by rival nations. Spacecraft adjust orbits when they're behind planets relative to Earth to avoid communication interference. Choosing when to act based on observer geometry is basic operational planning for any entity that understands observation networks. If 3i Atlas is artificial, and its operators understand that Earth possesses observational capabilities, minimizing detection during critical operations is exactly what competent navigation would look like. The October 29th perihelion also coincides with another important factor: the object's brightness surge and blue coloration. We've discussed how this brightness behavior doesn't fit standard cometary sublimation models, but consider what it would look like if an object applied significant thrust at perihelion. Depending on the propulsion method, chemical rockets, ion drives, even theoretical systems we haven't developed, you might see luminous exhaust, electromagnetic emissions, or radiation that appears as brightness increases and spectral shifts. A blue shift in particular could indicate high-energy emissions inconsistent with sublimating ice. I'm not claiming this is proven. What I'm saying is that when you observe an object brightening dramatically and changing colour precisely at perihelion, precisely when a solar obath maneuver would be executed for maximum efficiency, while simultaneously exhibiting non-gravitational acceleration afterward, you have a pattern that fits the artificial hypothesis at least as well as, if not better than, natural explanations. The natural explanation requires multiple independent unusual behaviours occurring simultaneously by coincidence. The artificial explanation requires one behaviour-controlled propulsion that produces all the observed effects as consequences. And here's the test. If 3i Atlas executed a reverse solar obath maneuver on October 29th to adjust its post-perihelion trajectory towards specific planetary targets, then its subsequent path should reflect that adjustment. It should continue exhibiting non-gravitational acceleration in directions that don't match random outgassing. It should maintain or approach alignment with planets of strategic interest, specifically Mars, Earth, or Jupiter. And its brightness and spectroscopic behaviour should remain anomalous in ways consistent with ongoing propulsion rather than passive sublimation. This is why the November-December observation window is so critical. We're not waiting years for data, we're waiting weeks. Between now and early December, 3i Atlas will either continue behaving in ways that suggest controlled flight, or it will revert to natural cometary behaviour now that perihelion has passed. The solar obath hypothesis makes specific predictions: continued anomalies, continued trajectory optimization, continued signs of non-natural acceleration. If those predictions fail, the hypothesis fails. If they hold, we're forced to take seriously the possibility that something is navigating through our solar system with intention. The mathematics of orbital mechanics don't lie. The efficiency gains from perihelion propulsion are real and well documented. What's controversial is applying those principles to an object we've classified as a comet. But classification is just a label. What matters is behaviour. And 3i Atlas's behaviour at perihelion, timed, dramatic and inconsistent with natural models, suggests we're watching something that understands physics as well as we do, and is using it far more skillfully. Which brings us to the next layer of improbability: the planetary alignments that shouldn't exist if this object is following a natural, unguided trajectory through our solar system. Probability doesn't prove causation, but it does tell you when you should start questioning assumptions. When the likelihood of multiple independent events occurring simultaneously drops below a certain threshold, continuing to call it coincidence requires more faith than acknowledging potential design. and when it comes to 3i Atlas's trajectory through our solar system, we've crossed that threshold. The probability that a random interstellar object on a natural unguided trajectory would approach Venus, then Mars, then align for significant gravitational interaction with Jupiter, all while exhibiting non-gravitational acceleration, is approximately 0.005% 1 in 20,000. Let me break down how that calculation works, because this isn't hand-waving speculation. This is published, peer-reviewed astrodynamics. The paper by Loeb, Hibbard and Crowell examines the orbital parameters of 3i Atlas and calculates the probability of its observed trajectory occurring naturally versus occurring through guided adjustments. The methodology is straightforward. You model all possible hyperbolic trajectories an interstellar object could take through our solar system, given its incoming velocity and direction. Then you calculate what percentage of those trajectories would result in close approaches to multiple planets within specific distance thresholds. For a truly random trajectory, the probability is vanishingly small. Space is big. Planets occupy tiny fractions of that space. Getting close enough to one planet to experience significant gravitational influence requires hitting a narrow geometric window. Getting close enough to 3 planets sequentially requires hitting 3 narrow windows in succession. The compound probability collapses rapidly. If 3i Atlas approached only Venus, that would be mildly interesting but not extraordinary. If it approached only Mars, same conclusion. But approaching Venus, then Mars, then Jupiter in sequence, that's when probability calculations start flashing warning signs. And we're not talking about flyby encounters at random distances. We're talking about approaches close enough that gravitational interactions become significant factors in trajectory evolution. Venus approach was close enough to measure gravitational deflection. Mars approach on October 2nd was close enough for detailed imaging by Mars-orbiting spacecraft. The Jupiter alignment sets up future gravitational influence that will affect the object's exit trajectory from our solar system. These aren't random near-misses. These are sequential encounters that suggest the trajectory was optimized for planetary interaction. Now, let's address the immediate objection. Couldn't gravity alone account for this? If 3i Atlas entered our solar system on a specific incoming trajectory, couldn't the Sun's gravity, combined with planetary gravitational influences, naturally bend its path toward these encounters without requiring any propulsion? The answer is mathematically no. Gravity is deterministic. If you know the starting conditions, you can calculate the entire trajectory. For 3i Atlas's observed planetary encounters to occur purely through gravitational dynamics, its incoming trajectory would have to be so exquisitely precise that even minor variations would cause it to miss one or more planets. The initial conditions required are themselves improbable to the point of straining credulity, but it gets more specific. The paper calculates that to achieve the observed trajectory using gravity alone would require the object's initial velocity vector to be aligned within a tiny angular tolerance fractions of a degree, and its incoming speed to fall within a narrow range. Natural interstellar objects don't arrive with such precision, because there's no mechanism to aim them. They're ejected from their home star systems through chaotic processes, gravitational interactions with giant planets, stellar encounters, supernova explosions. These processes impart random velocities in random directions. The odds that such a random process would produce an object aimed precisely enough to achieve sequential planetary encounters in another star system are, as calculated, 0.005%. This is where non-gravitational acceleration becomes critical. If 3i Atlas is applying even small amounts of thrust during its journey through our solar system, it can make course corrections that turn improbable encounters into probable ones. You don't need massive engines or Hollywood-style propulsion. Small sustained acceleration over weeks or months can adjust a trajectory enough to change a wide miss into a close approach, and the observations show exactly this. Consistent, directional, non-gravitational acceleration that correlates with trajectory adjustments needed to maintain planetary alignment. Let's consider what this would look like from an operational perspective. Imagine you're navigating an interstellar spacecraft into a new star system. Your primary objective is to survey the system's planets, looking for signs of life, resources, or strategic interest. You can't slow down enough to enter orbit that would require enormous energy expenditure, but you can optimize your flyby trajectory to pass close to multiple planets, maximizing observational opportunities. How do you do that? You calculate your incoming trajectory to get you close to the first target, Venus. As you approach Venus, you make small course corrections to ensure your post-Venus trajectory aligns with Mars. After Mars, you adjust again to set up your Jupiter encounter. At each planetary approach, you refine your trajectory using minimal propulsion to maintain the encounter sequence. This is called a planetary tour trajectory, and it's exactly how we design missions like Voyager, Cassini, and New Horizons. We use gravity assists and small propulsive corrections to visit multiple targets in sequence with minimal fuel consumption. It's efficient, well understood, and precisely what you'd do if you were exploring a star system with limited energy resources. And it's exactly what 3i Atlas appears to be doing. The 0.005% probability isn't Loeb's opinion. It's the mathematical result of modelling trajectory requirements and comparing them to the randomness of natural interstellar object origins. You can argue with the methodology. You can suggest that the calculations use overly narrow encounter distance thresholds, or make assumptions about incoming trajectory distributions that might be incorrect. But you can't dismiss the fundamental point. Achieving this trajectory naturally requires such specific initial conditions that calling it random requires believing in a level of coincidence that science normally rejects. And there's another layer. The planetary sequence isn't random in terms of scientific interest. Venus, Mars, and Jupiter are the most significant targets for studying planetary diversity in our solar system. Venus represents extreme greenhouse conditions. Mars is the prime candidate for past or present microbial life. Jupiter is the dominant gravitational force shaping the outer system and potentially harbouring life in its moons. If you were intelligently selecting which planets to approach for maximum scientific return, you'd choose exactly these three. The fact that 3i Atlas's trajectory optimizes for exactly these encounters suggests either extraordinary coincidence or deliberate selection. Probability analysis doesn't prove intent, but it shifts the burden of explanation. When natural explanations require compounded improbabilities, parsimony suggests considering alternative hypotheses. The artificial navigation hypothesis requires only one assumption, that the object is guided, and it explains all the observed trajectory characteristics without stacking coincidences. The natural hypothesis requires assuming multiple independent improbable factors aligned by chance. Which explanation requires more faith? This is the heart of why Loeb's claims deserve serious consideration rather than reflexive dismissal. He's not fabricating mystery. He's pointing at mathematical improbability already present in documented observations and asking whether we're intellectually honest enough to consider the simpler explanation. And that explanation leads directly to the next question. If course corrections were made, when would they be most visible? The answer is October 29th at perihelion, which is precisely when the object exhibited its most dramatic changes: brightness, colour, and trajectory adjustment, all occurring simultaneously during the one period when Earth couldn't watch directly. October 29th wasn't just another point on 3i Atlas's trajectory. It was the moment of maximum solar proximity, maximum gravitational acceleration, and maximum thermal stress. It was also the moment when the object underwent changes so dramatic that observers documented them immediately despite the observational challenges of viewing near the Sun. It brightened rapidly, shifted colour toward blue wavelengths, and transitioned from displaying an anti-tail to developing a more conventional tail structure. The most straightforward explanation is solar heating, triggering sublimation of specific volatile compounds, particularly carbon monoxide and diatomic carbon, which emit in blue wavelengths when ionized by solar UV radiation. This is a documented phenomenon in cometary science. Each of these changes individually would be noteworthy. Occurring simultaneously at perihelion, they demand explanation. Let's start with the brightening. Comets brighten as they approach the Sun because solar heating increases sublimation rates, producing more gas and dust that reflect sunlight. This is predictable and well modelled. You can calculate expected brightness based on solar distance, comet size, and composition. For 3i Atlas, the observed brightening exceeded model predictions. It wasn't subtle. Observers reported magnitude changes that suggested the object became several times brighter than it should have been given its distance and estimated size. That discrepancy requires explanation. Either the object is larger than calculated, more reflective than expected, or something beyond passive solar reflection is contributing to the brightness. The blue coloration is even more interesting. When comets brighten near perihelion, They typically show spectral signatures dominated by reflected sunlight and emission from sublimating ices, mostly neutral colours, or slightly reddish hues from dust. Blue coloration indicates specific chemical emissions, particularly from molecules like diatomic carbon or carbon monoxide, which emit in blue wavelengths when ionized by solar ultraviolet radiation. But as we've discussed, spectroscopic observations of 3I Atlas have been weak or absent in detecting the gas species that should produce blue emission. So what's causing the blue brightening? One possibility is compositional uniqueness. Maybe 3I Atlas contains unusual concentrations of carbon compounds that sublime at perihelion temperatures and produce blue emissions without generating the typical cometary gas signatures we're used to detecting. Maybe its composition is so different from solar system comets that our standard detection methods are missing the relevant spectral lines. This is plausible, but requires assuming 3I Atlas has a composition unlike any comet we've studied, which, given it's from another star system, isn't impossible. Interstellar chemistry could be different. Formation conditions around other stars could produce icy bodies with exotic compositions. But there's another explanation that fits the data equally well. The blue brightening isn't from sublimating ice, it's from something else. If 3I Atlas applied significant propulsion at perihelion, if it executed a solar obath maneuver using engines or drive systems that produce luminous exhaust, that exhaust could appear as brightness increase and spectral shift. Depending on the propulsion technology, you might see blue-shifted emissions from high-energy particle streams, ionized gas, or electromagnetic radiation. You wouldn't necessarily detect cometary gas signatures because you're not looking at cometary outgassing, you're looking at propulsion effects. I know how speculative this sounds, but consider the timing. The blue brightening occurred precisely at perihelion, precisely when a solar obath maneuver would be executed for maximum efficiency, and precisely when the object was behind the Sun relative to Earth, minimizing observation. If you're looking for a moment when an artificial object might risk revealing itself through propulsion signatures, this is exactly when you'd expect it, when efficiency demands maximum thrust and when visibility from Earth is minimized. The transition from anti-tail to tail is the third piece of this puzzle. Before perihelion, 3I Atlas displayed an anti-tail structure pointing toward the Sun, a feature we've already discussed as anomalous. After perihelion, observers noted the development of a more conventional tail structure pointing away from the Sun. This transition could indicate that solar heating at perihelion finally triggered sufficient outgassing to produce normal cometary tail formation. The intense solar radiation at closest approach could have broken through any insulating crust, allowing volatiles to sublime rapidly and produce the expected comet behavior. But again, timing matters. If natural processes triggered tail formation, you'd expect gradual development as solar heating increased during the approach to perihelion. Instead, observers report that the transition occurred relatively suddenly around the perihelion date. Sudden transitions suggest discrete events rather than gradual thermal processes. One interpretation: the object's surface properties changed at perihelion. Another interpretation: what appeared as an anti-tail before perihelion and a tail after perihelion are both artificial structures, not comet tails at all, but artifacts of propulsion or energy systems activating before perihelion and adjusting after perihelion. Let me be clear about the limits of this analysis. We're working with limited data. Observing objects near the Sun is technically challenging because of sky brightness and small angular separation from the solar disk. The observations we have are from professional and amateur astronomers working at the edge of instrumental capability. There's noise in the data, there's uncertainty in measurements, and there's always the possibility that mundane explanations account for everything once we have better data. But here's what we can say with confidence. Something changed on October 29th. The object's appearance, brightness, colour and structural features all underwent transitions that observers documented. Those transitions occurred at the one point in the trajectory where, if the object were artificial, you'd expect propulsion to be applied. And they occurred during the one period when direct observation from Earth was most difficult. That's not proof of anything. But it's a pattern that warrants serious investigation rather than casual dismissal. The question isn't whether 3I Atlas brightened and changed colour on October 29th that's documented. The question is what mechanism caused those changes. Natural sublimation requires assuming compositional uniqueness and sudden onset of activity despite gradual heating. Artificial propulsion requires assuming the object is artificial. Both explanations demand believing something unusual. The difference is that one explanation accounts for all the anomalies we've discussed: the trajectory, the planetary alignments, the non-gravitational acceleration, the October 2nd Mars encounter, and the perihelion changes with a single hypothesis. The other requires treating each anomaly as an independent coincidence. Which brings us to the prediction that tests everything. If 3I Atlas executed a solar obath maneuver on October 29th to adjust its post-perihelion trajectory, then specific observable events should occur during late November and early December. The object should continue exhibiting anomalous behavior consistent with controlled flight, rather than reverting to natural cometary behavior, now that perihelion has passed. We're not waiting decades for verification, we're waiting weeks, and that's where this entire investigation either validates concerns or resolves them definitively. Predictions are where speculation meets accountability. If Avi Loeb's hypothesis about 3I Atlas is correct, if this object executed a solar obath maneuver on October 29th to adjust its trajectory for optimal planetary encounters, then specific, testable predictions follow. And unlike vague, unfalsifiable claims about aliens that can never be proven wrong, these predictions have a verification window, November 29th through December 5th, 2025. Between those dates, we'll know whether the trajectory optimization hypothesis holds or collapses. Here's what the hypothesis predicts. If 3I Atlas is following an intelligently guided trajectory rather than a natural ballistic path, its post-perihelion behavior should continue showing signs of non-gravitational acceleration in directions that maintain or improve alignment with strategic planetary targets. Specifically, the object's trajectory should evolve in ways that keep it on an approach vector toward Earth, or set up optimal departure conditions relative to Jupiter. Natural comet trajectories don't do this once perihelion passes. Comets follow predictable gravitationally determined paths outward. Guided trajectories continue adjusting. The November-December window is significant because it represents the time frame when Earth's position relative to 3I Atlas becomes geometrically favourable for close approach. If the October 29th maneuver was designed to optimize an Earth intercept or close approach, the object should reach its closest point to Earth during this period. Orbital mechanics calculations based on the object's observed trajectory adjustments and non-gravitational acceleration suggest that late November through early December is when any Earth-optimized approach would occur. Now, Earth intercept doesn't mean collision. It means close approach, passing near Earth at a distance that allows for detailed observation or, in the artificial hypothesis, facilitates whatever objectives an interstellar visitor might have. For comparison, Oumuamua passed within 0.16 astronomical units of Earth, roughly 15 million miles. That's close on astronomical scales, but still far by human standards. If 3I Atlas follows a similar approach distance during the November-December window, it would confirm that the trajectory optimization we've been discussing was aimed at Earth. What would confirm the prediction? Multiple factors working together. First, continued non-gravitational acceleration in directions consistent with Earth approach, rather than random outgassing effects. Second, maintained anomalous brightness and spectroscopic behavior, indicating ongoing activity not explained by solar heating alone. Remember, the object is moving away from the Sun post-perihelion, so natural cometary activity should be decreasing, not continuing at anomalous levels. Third, trajectory evolution that matches models of optimal approach rather than natural gravitational trajectory. Fourth, any additional sudden brightness changes, color shifts, or structural alterations that correlate with trajectory adjustments rather than solar distance. Observation networks are tracking 3I Atlas continuously now. Professional observatories, amateur astronomer networks, and space-based telescopes are all monitoring the object's behavior as it moves away from perihelion. The data is accumulating in real time. By early December, we'll have weeks of post-perihelion observations showing whether the object is behaving as a natural comet should, or continuing to exhibit the anomalies that have characterized it throughout its approach. Here's the accountability mechanism. If the November-December window passes without any of the predicted behavior, if 3I Atlas reverts to natural cometary behavior, if its non-gravitational acceleration ceases or becomes clearly chaotic from random outgassing, if its trajectory evolves exactly as gravitational models predict without requiring course corrections, then the artificial hypothesis fails. Not because it was never worth considering, but because testable predictions didn't hold. That's how science is supposed to work. You make predictions, you test them, and you adjust your conclusions based on results. But if the predictions hold, if 3i Atlas continues exhibiting trajectory optimization, maintains anomalous activity, and approaches Earth during the predicted window, then we're forced to confront what that means. It means an interstellar object navigated into our solar system, executed a solar obath maneuver at perihelion while hidden behind the Sun, and approached Earth with a precision that natural processes cannot explain. It means we're not alone, and whoever built this object understands physics and navigation well enough to cross interstellar distances and operate in our system with clear objectives. The psychological weight of that realization is part of why institutional science is hesitant to discuss these possibilities publicly. It's not suppression in the conspiratorial sense, it's caution, born from understanding that extraordinary claims require extraordinary evidence, and that public discourse around potential extraterrestrial intelligence tends toward hysteria rather than rational analysis. NASA and the broader scientific community want to be certain before making any statements, and certainty requires more data than we currently have. But here's the problem with that caution. Opportunities are time-sensitive. If 3i Atlas is artificial and approaches Earth during the November-December window, we have a brief period to make detailed observations before it departs our system forever. Waiting for institutional consensus might mean missing that window. Waiting for perfect certainty might mean the object is gone before we mobilize sufficient observational resources to characterize it fully. This is Loeb's frustration crystallized when caution becomes paralysis. We risk losing historic opportunities because we were too careful to act while action mattered. What should you be watching for? Media reports of unusual observations between November 29th and December 5th. Statements from observatories or space agencies about 3i Atlas trajectory updates. Amateur astronomer reports on forums and social media documenting brightness changes or unexpected behavior. Any indication that the object passed closer to Earth than initial trajectory predictions suggested. Silence is also informative if the window passes without any unusual reports. That tells you the natural hypothesis is probably correct. But if you start seeing reports of anomalous observations, of trajectory adjustments, of unexpected close approach, then you're witnessing verification in real time. And here's why this matters beyond the immediate question of whether 3i Atlas is artificial. This situation is a test case for how humanity handles potential first contact. Not contact in the sense of communication, nothing suggests we're receiving signals or messages, but contact in the sense of detecting artificial objects from other civilizations in our vicinity. How do institutions respond? How transparent are they with data? How quickly does information reach the public? How does the scientific community balance caution with urgency? The answers to these questions during the 3i Atlas event will shape protocols for future encounters, because this won't be the last interstellar visitor we detect. As observational capabilities improve, we'll find more objects, and some of them will inevitably display characteristics that challenge our assumptions. The frameworks we establish now for transparency, for investigation, for public communication will determine how humanity navigates that future. So between now and December 5th, pay attention, not with credulity or assumption, but with informed curiosity. The data will tell the story. What we're waiting to see is whether that story ends with interesting comet, explained by natural processes, or unprecedented observation requiring new frameworks. One way or another we'll know soon, but before we reach that resolution, we need to understand why institutions might be hesitant to discuss these possibilities publicly, even when the evidence warrants attention. Let's talk about institutional hesitancy without devolving into conspiracy theories. When people accuse NASA or other scientific institutions of suppressing information about potential extraterrestrial objects, they're usually operating from a misunderstanding of how scientific institutions actually function. It's not that suppression never happens. History shows institutions have hidden, delayed, or misrepresented information for political, military, or bureaucratic reasons. But understanding why institutions are cautious about discussing objects like 3i Atlas requires understanding the incentive structures and risk calculations that govern organizational behavior. First, consider the consequences of being wrong. If NASA were to publicly state that an interstellar object might be artificial, and that statement later proved incorrect, the reputational damage would be severe and long-lasting. Every subsequent announcement would be met with skepticism. Credibility, once lost, is extraordinarily difficult to rebuild. For an institution dependent on public funding and political support, maintaining credibility is existential, so the threshold for making extraordinary public claims is set very high, not out of malice, but out of survival instinct. Second, consider the verification problem. When you're dealing with unprecedented observations, how do you know your data is correct? Instruments can malfunction. Processing pipelines can introduce artifacts. Human interpretation can mistake noise for signal. Before making any public claim about artificial objects, you need multiple independent confirmations from different instruments using different methodologies. You need peer review. You need internal scrutiny from skeptical colleagues actively trying to disprove the claim. This takes time, weeks to months, sometimes longer. During that time, you're sitting on data that you can't publicly discuss because it hasn't been verified to institutional standards. Third, consider the geopolitical implications. If an artificial interstellar object is confirmed in our solar system, that information has immediate national security relevance. Who controls that information? Who decides when it's released publicly? Do you brief the president first? Do you coordinate with international partners? Do you risk other nations claiming they detected it first and controlling the narrative? These aren't trivial concerns. The geopolitics of first contact, even passive observation of artificial objects, involve questions humanity has never confronted. Institutions default to caution when facing unprecedented situations because the cost of mishandling them is too high to risk. Fourth, consider public reaction. NASA's mission includes educating and inspiring the public, but it also includes not causing unwarranted panic. If you announce potential artificial objects without sufficient context, you risk triggering social disruption. People assume threat where none necessarily exists. Markets can react irrationally. Religious communities might interpret it through apocalyptic frameworks. Political actors might weaponize the information for their own purposes. Responsible communication requires preparing the public gradually, providing context, ensuring that experts are available to answer questions. Rush the announcement and you create chaos. Delay it too long and you're accused of cover-up. These factors explain institutional caution without requiring conspiracies. NASA isn't hiding proof of aliens out of malice. They're navigating an impossible balance between scientific integrity, institutional survival, geopolitical responsibility, and public trust. They're also bound by processes peer review, data verification, chain of command approval that weren't designed for time-sensitive discoveries. When those processes conflict with public curiosity, the result looks like suppression even when it's just bureaucracy. But let's also acknowledge where institutional caution becomes problematic. There's a difference between careful verification and gatekeeping. When institutions hold data that independent researchers could analyze and they delay release beyond reasonable verification periods, that crosses from caution into control. When transparency would allow broader scientific community participation in analysis, but is withheld to preserve institutional narrative control, that's suppression by any meaningful definition. The October 2nd high-rise image is a perfect example. If that image exists and shows nothing unusual, releasing it immediately would quell speculation. If it shows something ambiguous, releasing it with appropriate caveats would allow independent analysis and prevent accusations of cover-up. The only scenario where withholding makes sense is if the image shows something so clear that institutional scientists need time to verify it's not an instrument artifact before releasing it publicly. But even in that scenario, prolonged delay breeds distrust. Avi Loeb's criticism of institutional caution is rooted in this tension. He argues that the scientific method depends on transparency. The data should be public so the entire scientific community can participate in analysis, not just the small number of researchers with institutional access. He's right. Open science accelerates discovery and prevents errors that closed analysis might miss. But institutions fear that open science, especially regarding controversial topics like potential extraterrestrial objects, invites premature conclusions and public misinterpretation. Both positions have validity. The solution isn't choosing one over the other, it's developing frameworks that allow rapid data release with appropriate contextual warnings. Here's the observation, here's what we think it might mean, here are the uncertainties, and here are the alternative explanations. We're sharing this now so the broader community can participate in analysis. Conclusions remain uncertain. That approach respects public intelligence while maintaining scientific rigor. It's transparent without being reckless. The 3i Atlas situation is testing whether institutions can adopt that framework. So far, the results are mixed. Some data has been shared promptly. Other data, like the alleged October 2nd image, remains inaccessible or unreleased. Loeb's public statements and peer-reviewed publications are pushing institutions toward transparency by making it impossible to ignore the questions. Whether they respond with openness or defensiveness will reveal much about whether scientific institutions are prepared for an era when interstellar visitors become routine observations rather than rare anomalies. Here's the uncomfortable truth. If 3i Atlas is artificial, institutions might have known before the public did, and they might be managing information release strategically rather than transparently. That's not necessarily wrong, but it's not fully honest either. And in an age where trust in institutions is fragile, strategic information management looks indistinguishable from suppression. The cost of that appearance is public cynicism and erosion of trust in future institutional statements about space phenomena. The question is whether institutions recognize that cost and adjust their transparency accordingly, or whether they continue prioritizing control over trust and lose both. Which brings us to the final question. What comes next? Not just for 3i Atlas, but for humanity's relationship with the cosmos and our readiness to confront the possibility that we're being visited, observed, or simply passed by as unremarkable inhabitants of an unremarkable star system. We've come a long way from that opening question, what happened on October 29th behind the Sun, and now we're standing at the edge of something that's either going to resolve into mundane explanation or force humanity to confront a realization we've intellectualized but never truly faced. We're not the only intelligence operating in our cosmic neighborhood. The stakes of this moment extend far beyond one interstellar object. They touch on fundamental questions about who we are, where we fit in the universe, and whether we're ready for what comes next. If the November-December observations confirm that 3i Atlas is following an intelligently optimized trajectory, if the predictions hold and the object approaches Earth with the precision and timing that natural processes cannot explain, then we're in unprecedented territory. Not because aliens exist, that's a question with binary answers that doesn't change regardless of how long we avoid confirming it, but because passive detection of artificial objects creates different challenges than active communication or physical contact. We can't ask 3i Atlas what it wants. We can't negotiate or establish protocols. We can only observe, document, and wonder what purpose brought it here and whether it cares that we noticed. This is the scenario that keeps astrobiologists and SETI researchers awake at night, because it's the one we're least prepared for. We've imagined receiving radio signals, messages we can decode, attempts at communication that imply mutual interest. We've imagined physical contact through landing or direct interaction. But silent visitors passing through our system, observing us without interaction, conducting their missions without acknowledgement of our presence, that's harder to process. It suggests we're not interesting enough to contact, or worse, that we're being studied with the same detachment we apply to wildlife observation. It repositions humanity from protagonists in a contact scenario to background elements in someone else's exploration. And maybe that's appropriate. Maybe the Copernican principle applies to intelligence as well as cosmology. We're not special, not central, not the reason anyone would visit this particular star system. Earth is one of trillions of terrestrial planets. Our Sun is one of hundreds of billions of stars in the galaxy. If advanced civilizations are exploring or migrating between stars, we might be a waypoint, a curiosity, or simply one more data point in a survey of galactic planetary systems. The idea that we matter profoundly to interstellar visitors might be as geocentric as believing the Sun orbits Earth. But here's why 3i Atlas specifically matters, even in that diminished scenario. It's here now, it's observable, and it gives us the opportunity to test our detection and analysis capabilities in real time. Whether the object is artificial or natural, the process of investigating it reveals what we can and cannot do. It exposes gaps in our observational infrastructure. It tests our ability to coordinate international scientific efforts. It reveals how quickly we can respond to anomalous observations and whether institutions are prepared for transparency or default to control. Every lesson learned from 3i Atlas improves our readiness for the next interstellar visitor, the one that comes in 5 years or 50, when our capabilities are better and the observations are clearer. This is the long-term stake that transcends any single object. We're entering an era where interstellar visitors will transition from rare historic events to routine observations. The Pan-STARRS survey detected Oumuamua. The Atlas survey detected 3E Atlas. The Vera Rubin Observatory coming online soon will detect dozens or hundreds more. As our observational capabilities improve, as we survey the sky more thoroughly and with better sensitivity, we're going to find more objects moving through our solar system on hyperbolic trajectories. Some will be ordinary comets and asteroids ejected from other star systems, but statistical probability suggests some will be artificial probes, derelict spacecraft, or objects whose purpose we can't immediately understand. How we handle those discoveries depends on frameworks we establish now. Do we default to natural explanations until overwhelming evidence forces us to consider alternatives? Or do we investigate each anomaly rigorously with both hypotheses natural and artificial on the table from the start? Do we prioritize institutional control over data, or do we embrace open science that allows independent researchers to participate? Do we communicate uncertainties honestly with the public, or do we withhold information until we're certain? The answers to these questions will determine whether humanity approaches potential first contact with transparency, wisdom, and preparedness, or with confusion, distrust, and missed opportunities. And then there's the personal stake, the one that exists regardless of institutions, regardless of whether 3I Atlas is artificial or natural. We're living through a moment when the question, "Are we alone?" might transition from philosophical speculation to answered question. For millennia, humans have looked at the stars and wondered. We've built mythologies around celestial visitors. We've imagined ourselves as the universe's only intelligence, or as one among many. But imagination and confirmation are different experiences. The psychological and cultural impact of knowing truly, knowing that intelligence exists beyond Earth, would reshape human civilization in ways we can't fully predict. Some people will experience it as relief validation that the universe is alive with complexity and meaning beyond our small existence. Others will experience it as threat fear that intelligence capable of interstellar travel might view us as we view less developed species on our own planet. Still others will experience existential disruption, the collapse of religious, philosophical, or cultural frameworks that assumed human uniqueness. There's no single correct response, but there's value in preparing emotionally and intellectually for the possibility that confirmation comes sooner than we expect, and in forms we didn't anticipate. Which brings us back to you, watching this now, processing what we've discussed over the past 40-some minutes. What do you do with this information? First, you stay informed. Between now and December 5th, follow observational reports. Watch for announcements from observatories, from NASA, from independent researchers. Look for trajectory updates, for brightness anomalies, for any indication that 3I Atlas is behaving in ways that confirm or refute the artificial hypothesis. Be critical of sources, verify information. Distinguish between documented observations and speculation, demand evidence. Second, you participate in community discourse. Comment on this video with your thoughts, your observations, your own research into the topic. Share it with others who think critically and demand evidence. This isn't about building conspiracy theories. It's about building informed communities that can process complex scientific information together and hold institutions accountable for transparency. The more people watching, questioning, and demanding access to data, the harder it becomes for information to be gate-kept or suppressed. Third, you manage expectations. The most likely outcome is that 3I Atlas is a comet with unusual but ultimately explainable characteristics. Most anomalies in science resolve into mundane explanations once we have better data. That doesn't mean the investigation was worthless. It means we learned something about the boundaries of natural phenomena and we improved our analytical capabilities for next time. Don't invest so much hope or fear in the artificial hypothesis that you can't accept natural explanations if they prove correct. But if the predictions hold, if December arrives, and the data shows continued anomalies, continued trajectory optimization, continued behavior inconsistent with natural comets, then you're witnessing something unprecedented. You're watching humanity take its first confirmed steps into a cosmos populated by other intelligences. You're part of the generation that transitions from wondering to knowing. And that's a responsibility as much as an opportunity to handle that knowledge with wisdom, to resist both panic and dismissiveness, to think clearly about what it means and what comes next. On October 29th, 2025, something happened behind the sun. We don't yet know what, but we're about to find out. And whatever the answer, the fact that we're asking the question seriously, with data and mathematics and institutional resources dedicated to finding truth rather than confirming assumptions, that alone is progress. That alone suggests humanity might be ready for what comes next, whatever that is. The universe doesn't care whether we're ready, but we owe it to ourselves to try. Stay curious, stay critical, and watch the skies, because between now and December, they might tell us something we've been waiting our entire existence to know.